Bismillahirrahmanirrahim. This is the equation that we had derived for 2D elasticity problems. On the left hand side we have the K matrix. This part is the elemental integration, and after doing this for all the elements, they all have to be integrated using the connectivity table, and this then becomes the system displacement matrix with all the nodal displacements of the system. On the right hand side we have four components. The first three, namely the force vector because of temperature, body force vector, and the pressure force vector, they have to be done on the elemental level. All elements have to be dealt with in the same way, and then all have to be assembled again using connectivity table, and this is where it shows. And once the whole F matrix has been constructed, at the last step the nodal forces, if they are acting anywhere, they are added at the end. They are not involved in the summation process. Now some explanation for this. This is for the plane stress case. For plane strain case, instead of this part here, we use this one. We derived this in our last class. For the body force vector, if a body is subjected to x and y body forces, that is, it is subjected to force somewhere from, this is the element, and the force is being applied, the body force is being applied from somewhere here. So there's an x component and a y component. Then on the three nodes, we apply the x component on the three nodes like this. Volume multiplied by that component divided by 3. Actually you are dividing the body force into three parts. The x-axis part divided into three parts and then applied on the three nodes. Similarly, the y-axis part also gets divided into 3 and then applied to the respective nodes. If x or y happens to be 0 in some case, then that component will simply disappear. This one is the pressure force vector. Now this is the special case of pressure force being applied on nodes I and j, on the ij side. So we can, by superposition, we can divide this into a pressure force in the x direction plus a pressure force in the y direction, and from there you get the components px and py. And again the thinking is the same. You apply this pressure force, which is in Newton per square millimeter. This x and y, these were in Newton per cubic millimeter, so you had to multiply them with the volume. Here you are simply going to multiply them with the area. This t, thickness of the element, this element has some thickness t, and this L, ij shows that its length ij that we are talking about, not length j, k or ki, because no pressure is on these faces. So you multiply this pressure force with the area, you get something in Newton. You divide by 2, not 3 this time, 2, because you are going to apply it equally on the two nodes which are relevant. No force gets applied here. Now similarly, just as was the case in the body force, the px, the x component will be calculated by multiplying this px with the area, and then you apply half of each on the two nodes. Similarly, the y component, that gets applied here. So this was the last lecture, and now if we apply this knowledge to to a problem or two, let's consider this problem. There's a component with a thickness 0.2 millimeter. So this has this dimension. This is 0.2 millimeters, and there's a pressure force applied here, a concentrated force here, a concentrated force here. These are the constraints. Now this problem is a big problem to be solved on paper. Unlike 1D problems, which we could solve from start to end, very few 2D problems can be solved from start to end, but we'll just solve the relevant part. Let's say we take this element 1, and this is shown in a magnified form here. These are the ijk nodes, these are the x and y components of the spatial components, that is the coordinates. So this has location 4 1, x-axis 4, y-axis 1. Similarly, somewhere around here you will have origin somewhere here, so that doesn't matter. So the part of the forces that are being applied on this element only are taken. This part comes, this force comes. Similarly, other elements will be taken one by one, but we'll just focus on this one for now. Now, to start with, we are going to apply all this knowledge to this problem and see where it takes us. Now, to start with, is this a plane stress case or a plane strain case? Now, it's obvious that the thickness is 0.2. It's a very thin plate, and there is no mention of any constraint on this face or the opposite face, so it's a free plate. And if you consider the in-plane dimensions, if this is 2 millimeters, these are all in millimeters. These are millimeters. This is 2 millimeters. This is also 2 millimeters. So if 2 millimeters, 4 millimeters, 5 6, at least 5 6 millimeters is here. Similarly, height is ample. As compared to these dimensions, this is very small, and also there is no mention of constraint. So this is a plane stress case. So this will be very important, because while using the formulas, we'll be using those for plane stress. Now, if we start with the K matrix, if you recall, it doesn't matter, K matrix for the element, it has, if you recall that this was the expression. Now, we had not completed this expression, we had not extracted the final form of this, because it all depends on this D. Now we know that it's plane stress case, so now we can proceed. So we need to find out B, and then B transpose will automatically be known, and then T and A. T is given. What about A? Let's start with A. You recall from one of our previous lectures that A is simply you all have these dimensions, so there's nothing difficult about it. Just put in the values, and if we solve this, the answer comes out to be, you can verify it for yourself, it's 4, and it's actually square millimeters, but this is the value of 2A, so obviously A will be 2 millimeters square, half of this. Now, the next thing that we take up is the B matrix. B matrix, if you recall again from one of the previous lectures, was simply this was the B matrix. Now, to calculate these, this is very simple. Bi again from one of our previous lectures. This is yi, yk, yj, yk, 1, 1. This is yk 1, comes out to be 2. Similarly, bj yk yi now in this case, yk yi yk1 yi1 again, this comes out to be 0. bk k yi yj. This is -2. Similarly for c, again recall the formulas. This is -1, cj, j, so we'll start with k. This is 2 plus 2, and ck, the last one. K, so xi, xj, 1, 1. -1. Now recall the checks. B's add up to 0. So that's a good indication we are doing it right. C's add up to 0. Again, we get confidence that we are not doing it wrong at least. Now, B is simply 1/4 and just put in the relevant 2, 0, 0, 0, -2, 0, 0, -1, 0, 2, 0, -1, and now you just -1, 2, 2, 0, -1, -2. This is the B matrix. Now if we recall that we are using the plane stress case, and K matrix, the D matrix, I beg your pardon, the D matrix for plane stress case, which is this case, is this. And if we put the values, we get 210 is 3, 1 minus 0.3 square, 1.3.310000, and here we get 1 minus 0.3/2. And if calculated, this becomes, you need to verify these values for yourself. This is the D matrix for plane stress case. Now K, now we are in a position to calculate K, B transpose, D, B, T, A. All of these values we know. A is 2 millimeter square. B we have calculated. V transpose, automatically we get. D we know. So if we solve it, we can get the value of K. I'll leave the student to complete this expression and then find the value of K. Now, while I won't be doing K here, I'll remind the students that we always have different checks to find out if our K's are all right or not. So let's recap those here. Checks. Number 1, K should be symmetric. Whatever K you get, it needs to be symmetric, or otherwise it is not right. 2, the diagonal elements, whatever this is the diagonal for diagonal element for K, diagonal must be non-zero, and usually they will be large as compared to the other values, but at least they will not be non-zero, and let's call it non-negative. they are also usually dominating, but as far as conditions go, they should be non-zero and non-negative. There will not be a negative number on the diagonal of the main diagonal of the K, and there won't be any zeros. And number 3, all rows and columns must add up to 0. This is also a good check. When I talk about diagonal, I should write the main diagonal. There are many diagonals in a matrix, so this takes care of our K matrix. Now there's still work to be done. This is just first part of the problem. If I remind you, we have only calculated till now this part, and if we can calculate this part for this element, then we can calculate for all other elements too, and after that it's simply a matter of assembly, which can easily be done by the connectivity table. Now the next step that we need to do is to calculate the force vectors. Now there is a concentrated load here. One will deal with that in the end, but there is a temperature component and there is a pressure component because no body forces are there. If we again look at the problem, there is a pressure component here, and then there's a concentrated load, but this usually is done at the end. This is there, and then there's a temperature rise. So we need to do both of these things one by one. Let's take the pressure part first. The expression for Fp was, we did it last time again, let's refer to that here. T length over 2, and then we have to be very careful where we put the zeros. And in this case, because again, as our formula was based on this diagram, so we have a pretty similar situation here. I and j is the relevant side, so for the k there will be zeros. So it's very simply again over 2, and then we have px, py, px, py, 0, 0. This is the expression. Now what about px and py? This is the situation. This is the p, or you can say, let's say this is p. All you need to do is you need to find out this px, x component, and py, y component. If theta is here, then this is also theta. So basically px is equal to p sine theta, and py is equal to p cos theta. Now what about the thetas? If we consider the tan, it comes out to be 2 over 1 for this, and theta is equal to tan inverse 2, which is 63.43 degrees. So if we calculate these, if you put in the values here, px comes out to be 8.94 Newton per square millimeter, simple trigonometry, and py comes out to be 4.47 Newton per square millimeter. These are the values. So we have taken care of px and py. What about the length, Lij? Again we have this is I node, this is j node. We know the coordinates of the two, 4, 1, 3, 3. So Lij is simply 4 minus 3 whole square plus 1 minus 3 whole square. This is the length, and this comes out to be 2.24 millimeter. Now we have the thickness, we already know. Just put in the values. 2.24 for this, thickness was 0.2 over 2, and here just put in the values of 8.94, 4.47, 8.94, 4.47, and then 0 and 0, because we're talking about this I node and J node. This here there's K node, but that is irrelevant as far as the pressure is concerned. So FP is this. Now if we can simplify it, multiplying these values, and this turns out to be 2 1 2 1 0 0, the same thing. You should just multiply the values. So what is the next step? The next step should be the calculation of the force vector because of this temperature change. Let's take that up and recall that this is the plane stress situation that we are talking about. Talking about the force vector because of temperature. Now that was E alpha delta dt over 2 minus nu bi ci b j c j b k c k. Now these are, we are already familiar with these. E we know, alpha given to us, delta t is given, so everything is given here. There's no problem at all. 210 raised to the power 3 into alpha was 12 into 10 raised to the power minus 6, delta t 50, thickness 0.2, thickness was 0.2 over 2 1 minus 0.3, and the values of bi ci etc are also known to us, so that comes out to be 2 minus 1 0 2 minus 2 and minus 1. These we all calculated when we found the B matrix. So this is these are the values, and if you simplify them, this is your final expression. We just multiplied these values with each other, and this is the, now there's, in this question there is no body force involved, but if there was a body force we could have easily dealt with using the formula for body force, so that's not a difficulty. Now or we can also just to put it in writing, there is no body force vector, so that's 0. So now if we add the right hand side together, because all of them get added together, these three, this is 0, but these two get added together, and then you get a force vector for one element, and then you have to then assemble it over the whole body for element number 1 to element number e. But since we don't have all the elements here, we're just showing for one element, so we have to add them together, and that will be f. Total f will be for this element, again I have to mention element here, will be 2 1 2 1 0 0 plus 17.14 2 minus 1 0 2 minus 2 minus 1. This will give us the force vector for one element. Now we have to basically repeat the process for all the other elements, like this, and once we have all those values, then using the connectivity table we add all this together using the connected rule. And once that is done, only at the last step, let's say this, and in that case we'll get a system matrix. This is element level. Similarly, you'll get plus many, in fact all other elements you do. Then you will add them together using the connectivity table. This will give you a system equation. And at the last step, let's say this is that equation, that force vector, that is a result of the assembly. At the very last step, you will add this concentrated force vector, this one. For example, here you will add this, then you'll add this one also. So if the degree of freedom for this in the whole system is, let's say 3, let's say we start numbering elements from 1 2 3 4, if this is 3, then at the third spot, this is the result of this assembly, and at the third spot here you will write, obviously if this is the node number 3, then recall that the degrees of freedom for this are 5 and 6, 5 in the x direction, 6 in the y. So this should take the 6th place. 1 2 3 4 5, and the 6th place you will write 20 Newton. You must not make a mistake of adding these two and then adding this one also, this 20 Newton force here, because if you do that here and you do the assembly later on, then this 20 Newton will also be a part of this element and this element. You will add them all together, it may become 60 Newton. So that is why we take this step at the end. Similarly for this one, this will also occupy some place here, so you should be wary about this. So this step always comes at the end. At the end, add any concentrated loads at their appropriate degree of freedom. So this completes the first part of this problem. We were able to make the K matrix for the element, and then we were able to calculate the initial force vector because of temperature, and the body force was 0, and the pressure force vector. This one is initial force, and the pressure force is this one. And after the assembly, that is, all the K matrices will be assembled together, all these matrices will be assembled together, this part, and at the end you will add the concentrated force vector, and then you get the right hand side completed. Once this is done, obviously you apply the boundary conditions. After this, boundary conditions are applied, because without boundary condition you cannot solve the problem. And boundary conditions in this case will be, obviously, this node, this node, this node, and this node. All these 4 nodes will be constrained in the x and y directions. And you cannot apply constraints here. You have to apply constraints just like the forces can only be applied at the nodes. The constraints can also only be applied at the nodes. So once you apply the boundary conditions, after the complete system equations are made, then you solve for use. You get the use for all. And once you get the use for all, obviously then you can calculate the strains. And number 4, the stresses, the final step. So this is the scheme. So we are not going to do all these here. takes a long time for that. Just imagine how much time we took for one element. uh, Imagine how much time we will take for all these elements, and when we combine them together it will be a very big K matrix. We won't be able to solve it on paper, but it's difficult to solve on paper, that's all. It's not difficult to understand, and if you have a computer it's very easy to do. So we'll just stop here and imagine that we have reached this step. Boundary conditions very easy to apply, but before that you have to assemble the whole system, which is very difficult to do on paper or board. Let's say we did that and then we applied boundary conditions and then we solved for u's, that is, we got all the displacements of the system. Now how to proceed from this step onwards. Now imagine that as a result of that solution, we now know all the displacement values at all the nodes in the system. All nodes, u and v values we know. Now if we know all the node displacements, then we also know the displacements of these the element that we just considered here. So let's talk about this element. This is the element number one. We have three nodes and each node has a u and v value. Let's say these are those values that we have calculated. Now how to calculate strains and stresses? The next step, we skipped the part here and I explained that, but the next we can do again easily. How to calculate the strains? It's very simple. The strain vector is nothing but this, and this is done at the individual, again it is done at the individual element level. So there's nothing difficult about this. We know the values of the B matrix, all the values. This is just, I'm just copying from the part we did earlier. Here, I just copied it from here. And for this element number one, we're talking about element, so we'll be calculating strains and stresses at the element level. So element number one, I, j, k, this is the sequence counterclockwise, and this is ui, vi, uj, vj. So we just put in the values 2, 0, 0.5, 2, 1, minus 0.5, and don't forget that these are all in very small values. So if you calculate this, you get the strain values. Now I am hoping here that all of you now understand that even if I write epsilon here, it means total, because recall that these u values have been arrived at after adding the temperature effects. So this gives us the total strain, not the mechanical strain. Now because we are going towards the calculation of stresses, we have to now subtract those parts of the strains that are not mechanical in nature. So for that, recall this plane stress case. So alpha delta t 1 1 0, just put in the values. This is 6 into 10 raised to the minus 4, 6 into 10 raised to the minus 4, and 0. This is for plane stress. You have to be very careful about these things. Now what about this mechanical strains? Those will be total strains minus initial strains, and that, if you subtract the two, you need to verify all these calculations yourself. This is the, and once we have reached this stage, now the last step is very simple. Last step is calculation of stresses. The stress vector is nothing but d. Again, this is I need to write mechanical strain. This one, not this one. So if we again refer to our original values of the D matrix, that will remain the same. 1.3, 0.31, 0, 0, 0, 0.35, and here the value should be -1 into 10 raised to the power -4, 5.25 into 10 raised to the power -4, -0.25 into 10 raised to the power -3, and the values come out to be 12.6510. Again, please verify these values, don't take my word for it. This is the stress vector. Obviously this is sigma x, sigma y, tau xy. Now it's a plane stress case, so the stresses are only in this plane, the plane of the problem. So these are all the stresses we are going to get, but the strains, there's an extra strain outside these values that we have three strain values, but there's another strain value which is perpendicular to the plane in the direction of thickness, and that strain is epsilon z. Recall that we have discussed that epsilon z value can easily be calculated by using this formula. And this is nothing but the third equation of the generalized Hooke's law, which includes the temperature effects, and then putting sigma x is equal to 0 because sigma z is equal to 0 because there is no stress perpendicular to the plane of the paper. So just put in the values here, and you should get 0.3, 200, 10 raised to the power 3, epsilon x, epsilon y we just calculated, 12.65 plus 108.9 plus alpha delta t again, 12 into 10 raised to the power -6 into 50. Now it's very interesting. If you get this total value, it comes out to be 4.18 into 10 raised to the power -4. This is the value, final value. So this includes the effect of the thermal strain. If you just want the mechanical strain in that direction, what should that be? I leave that for you to consider. So this is the end of our question, and that is the end of this session too. Thank you very much.